Okay, now let's do some examples. Question 1. So what's happening is we have a coil in the, we have a AC alternator. Okay, that's what's happened there. And now, if you have a look, we have the flux over time graph, and they ask me to find the voltage and time graph. Okay, if you read the basic principle, okay, so now there are 40 tens of coils, and the induced EMF is 2, the voltage, 2 volts RMS. Okay, so the RMS value is 2 volt. So when I try to sketch the graph here, okay, I need to know the peak voltage. Okay, so remember your equation. Okay, so your peak voltage is basically the average value, RMS value, times square root of 2, okay, a magical number. So do it in your calculators. So 2 times square root of 2 is going to be 3, approximately. Just do it now. Okay. 2.8. This is your peak value. So when starting the graph, okay, label 2.8, okay, which is your peak value here. Okay, then let's start doing the graph. Remember, okay, also minus. Okay, let's put it down here. Minus 2.8 volt, which is the peak value. So, yep. Okay, remember your Faraday's law. Okay, Faraday's and Lenz's law. Okay, initially, it's zero. It has. Let me write down it here. So, the induced EMF is basically inverse. The the inverse of the rate of change of the flux and time graph. Okay? So, yep, initially at this point, okay, the rate of change is maximum is positive, okay, but with a minus sign in the front, it becomes a maximum negative. So initially it starts from here. So at this point, okay, the rate of change is 0, so it's going to be 0. So at this point, it's decreasing, okay, and the rate of change is minus, but with an additional minus in the front, so it will be positive. Okay, so positive here. So just let me make it clear. If the graph goes this direction, okay, the gradient is greater than 0. If the graph goes at that direction, the gradient is less than 0. It's a minus number. Okay. Now here the gradient is flat. At the turning point, the gradient is 0. Okay. So when the gradient is 0, 0, the gradient is positive maximum, but with a minus sign in the front, it becomes negative. Okay. So do the same thing. Yep. For every individual important point. And then you will find, yep, then you will, then you will you will have your graph. Okay, so when we're connecting the graph, remember it's a sine wave, so don't draw straight lines. If you draw straight lines in this type of question, you get 0 marks. Okay. Always remember the sine waves or cosine waves. With a peak voltage of 2.8 volt down. Yep. Now, in term, well, look at this question in terms of loop rotating a magnetic field. Okay. Yep. So, which one is true? The induced current is at maximum when the flux through the loop is at minimum and the plate of is perpendicular to the field. So, yep, with the AC alternator. Okay, so if you look at your nose, and let's go back to the nose. If you go back to your nose, yep, here, okay. So the flux is at maximum. Sorry, the voltage is at the maximum when when the coil is perpendicular to the magnetic field at points, parallel to the magnetic field, okay, at position 1 and position 4, okay, here. So it's when the coil is paralleled. So in this case, A is wrong, okay, because it says perpendicular. Okay. And also maximum, yep. Now, yep. Let's look at the front. Okay, the maximum voltage when the flux through the loop is a minimum. So if we look at this statement, the maximum voltage occurs when the flux is actually 0. It's not the minimum. Minimum is minus number. Yeah, there's something wrong with this question. What they mean is when the flux through the loop is 0. Okay? That's what does the question mean. But however, statement 1 is wrong because of this perpendicular. Okay? Question 2 is also wrong. Yep, because the perpendicular, wrong. One of these has to be right. The induced current is at maximum when the flux through the loop is at minimum, so C will be right. D will be wrong because it's not, induced EMF, okay, is related with the change of flux. Okay. It's not flux itself, magnetic flux, so C will be your right answer. Okay. The induced voltage is at maximum in an AC alternator, in a looping, rotating, yep, the AC alternator. Okay. When the flux is minimum, it's 0, not minimum, it's 0. Okay. Because when the magnetic flux is 0, the rate of change of magnetic flux over time on the graph is a maximum. Okay. And that's when the loop is parallel to the magnetic field. Now, look at this question. So in this question, we have AC alternator. I can tell this is an AC alternator because if I look at those rings, they sleep rings. They're not commutators, they sleep rings. When I say sleep rings, they are AC alternator. Yep. DC would be commutators. Okay. So, yep, it goes, well, figure 4, the question asks me which one is right, which one is the voltage, which one is the flux. Okay. Have a brief look. Have a brief look at those. Question A reasonable. Question B is not reasonable because if you have a log, the voltage should be the rate of change of magnetic field, and it doesn't. It's not. So say it's not. The magnetic flux never. The magnetic flux graph never overlaps the voltage graph. D, no, it doesn't work. No overlapping. So A must be the correct answer without even testing them. So if you want to test them, uh, so the magnetic flux for A here is, yep, will be maximum. So the voltage will be will be zero, zero. The gradient is minus. Remember Lenz's law. So let me write it down again. The gradient of the dotted line is minus, but if we put a minus in front of it, it will be positive. Positive maximum. Here, minimum, minimum flux, zero, zero flux. Positive gradient with a minus sign in front, it becomes minus. So the question A makes sense. Okay. The other doesn't.